So this lesson is sort of the final piece in tonight's lesson. It really ties together several of the last few things that we've done. When we did disk method problems, we were revolving something around an axis and the cross sections were circles. When we did washer method problems, we revolved something around the axis and the cross sections were washers, and we had to visualize that. We had to figure it out. In these problems, they're just going to tell you, hey, the cross sections are squares. Or, hey, guess what? The cross-sections are triangles. Or, hey, guess what? The cross-sections are quarter circles. And that means we're going to have weird shapes. But the reality is one of the things that makes these problems a little bit easier is that they just tell you, hey, look, they're squares. I sort of want to draw a picture of one of these for you right now, and I don't know how good it's going to be, but we're going to try that before we go into the examples. So let's say, for the sake of argument, that I have a region that looks like this. So that's the region I'm working with. And let's say they tell me that the cross-sections perpendicular to the x-axis are squares. So presumably this is y-axis, this is x-axis. So my cross-sections perpendicular to the x-axis are squares. So this shape, when I cut it this way, is supposed to give me squares. So you imagine you're looking at your screen. Imagine that sticking out of your screen are a bunch of squares. The natural question is, well, I think the natural question is, how far do they stick out of your screen? And the idea is, well, they're squares, right? The first one here, if it's that tall, then it's sticking out of your screen that much. As I move along, if this next one is that tall, well, then this one is sticking out of your screen that much. Right, this one here, is a little bit further, and so it's sticking out of your screen a little bit further. Right. Over here you've got another one. Right. And I mean, every one in this thing you've got squares that are sort of sticking out of your screen. And as I go over to this side, this back side gets smaller, so they stick out of the screen a little less far, and a little less far, and by the end you've got these teeny tiny little squares that you can barely see. It's really a pretty decent picture there. Again, what does that thing look like? What is the thing? I don't know, but we want to know if we can find the volume of it. And what I want to remind you of is when we did disk method problems, we did the integral of pi r squared. And why did we do that? We did that because the area of a circle is pi r squared, and we were adding a bunch of circles. When we did washer method problems, it was pi times big R squared minus little r squared. We did the integral of that because we were doing a big circle minus a little circle. With all of these known cross-sections, every one of them is just going to be the integral of the cross-section area. And it now may make sense why we had the first video we did in the sequence, talking about the areas of all these random shapes were. So let me get into the examples so we can actually see one of these happening. So let the region R be bounded by y equals x squared. I've got x squared drawn, and y equals 1. I've got that drawn. I want to write an integral expression for the volume of a solid with that base whose cross-sections perpendicular to the x-axis are squares. So kind of like we had on the previous one, you imagine you've got these sort of squares that are sticking up off the region. And as we go along, the larger that the base section is, the further out of the screen the things are coming. I want to add up that whole thing and figure it out. In some sense, our steps are very similar to what they were before. Your first step should be thickness. Is this going to be a dx or a dy integral? And what you're going to do is, it's just like the revolutions. When we revolve things vertically around a horizontal axis, when things were done up and down, we did things in terms of x. So this is dx. Another way of thinking about that, when they say it's perpendicular to the x-axis, it's going to be dx. Later in the video, when I get to things perpendicular to the y-axis, it'll be dy. Our second step before was to identify the radius. In this case, I kind of want us to identify the formula that we're going to be working with. In this case, I'm working with a square, and the formula for the area of a square is side squared, right? So our integral is going to look like the integral of side squared dx. And the question becomes, what is the side length of these squares? And again, this really ties in now the second lesson. What's the side length of these squares? What is the length right here? Well, it's simply the distance between this and this, right? Because this is a vertical distance, I want to subtract two things that are y equals. Hey, look, I have y equals x squared and I have y equals 1. That side length, the side length for us, is 1 minus x squared. Right? The third step that we take is to find bounds. Because this was an x integral, it's going to go from where we started at -1 over to where it ends at +1. So these bounds go from -1 to +1. And step 4 is sort of where we tie it all together. I mean, we, write the integral. Right? So I'm going to have this integral from -1 to 1. We set up here that it was supposed to be side squared. So my side measurement was 1 minus x squared dx. Note, I don't need a pi out front because the area of the square had nothing to do with pi, right? So that's just it, right? I want to throw one more example of this in here really quickly. What if I had asked you to do semicircles, right? What would that change, right? It doesn't change step 1. Step 1 still is dx. It wouldn't change step 3. Step 3 still tells us we're going from -1 to 1. Right? The only thing that really changes is step 2. Right? Step 2, the area of a semicircle is 1/2 pi r squared. So the question is, what is the radius of one of these circles? And the best way to do this is to sort of look at the region and draw it in. If you're looking at a region that looks like this, so this is our, y-axis, x-axis. The cross-section is perpendicular to the x-axis or semicircle. So you're sort of like drawing this way and getting a semicircle. Drawing this way, semicircle. Cutting this way, semicircle. Cutting this way, semicircle. You're getting all these semicircles on here. What is the radius of one of these semicircles? Well, the radius would be half of whatever that distance was before. So the distance before was 1 minus x squared. We're doing half of that. Right? So when you finally get to step 4 and you're setting up this integral and you're doing this thing, we're going to have the integral of 1/2 pi r squared dx, where the radius is this. And my bounds go from -1 to 1. And I mean, yay, that's the setup. We can pretty that up a little bit. I can pretty that up by sort of squaring this 2 here and bringing that out. I could end up with 1/8 pi, integral from -1 to 1. And all you'd have in here is 1 minus x squared dx. I was going to get into the y equals problems, but I'm already really long in the video here, so I'm going to stop it here. I hope that made enough sense. If not, go back and try and process these again, but we'll definitely talk about them in class tomorrow. So I'll see you there.